Good morning, everyone. I'm Federica Salanitri from the University of Catania. Today I'm presenting our recent work on multiple sclerosis lesion segmentation. Why is MS lesion segmentation difficult? Three challenges. Lesions are tiny and scattered, morphologically variable, and irregularly distributed. This is why radiologists still annotate manually, which is time-consuming and variable. Existing approaches have clear limitations. CNN-based miss fine-grained boundaries on small lesions. Transformer-based are more powerful but computationally expensive and require massive dataset. Foundation models like SAM are promising, but rely on manual prompts and impose prohibitive computational costs for clinical deployment. AutoSAM attempted to automate prompt generation, but still requires SAM at inference, keeping the computational burden high. The question becomes, how do we extract the capabilities of large models without the computational burden? Our idea was to use SAM only during training to teach a neural network how to automatically recognize MS lesion patterns. Then, at inference time, replace SAM with a lightweight model that already knows what to do. So we divide the training into two phases. In phase 1, we train a dense prompt learner with a frozen SAM. The network learns to self-discover which spatial information is most important for recognizing lesions. After phase 1, we wanted to understand what the dense prompt learner had actually learned. So we visualized the 256 prompt maps generated during training. Looking at the figure, the second column shows a sample of 4 out of these 256 learned prompt maps. The third column shows the average of all 256 maps. And what's fascinating is that this average representation captures the semantic structures needed for accurate lesion segmentation. You can see how it directly correlates with the ground truth segmentation mask shown in the last column. This was the key insight. The network had learned to encode spatial and contextual information that was sufficient for accurate segmentation entirely on its own. We realized that we could replace SAM with something much simpler because the dense prompts contained everything we needed. Based on this discovery, we moved to phase 2. We trained a small convolutional module, the aggregator, to learn how to transform these learned embeddings directly into segmentation masks. The key idea is to replace SAM with this lightweight decoder. We take the intelligence encoded in the dense prompts and compress it into a much simpler model. The result is a model that weighs 100 times less and runs 15 times faster than SAM. This gives us the efficiency we need for clinical deployment while maintaining accuracy. We evaluated our approach on the MS-LESSEG dataset. Zero-shot foundation models struggle with MS lesion complexity. Even when adapted for medical imaging, they lack task-specific knowledge. AutoSAM that attempts to learn prompts automatically perform better, but still rely on SAM at inference, so limiting the accuracy and efficiency. Our model achieves superior performance across all metrics. This demonstrates that learning dense prompts and decoupling from foundation models at inference enables precise lesion delineation. The difference becomes even more evident when you look at the visual results. AutoSAM manages to detect most lesions, but the boundaries are often coarse and imprecise, with limited anatomical fidelity. To assess generalization, we extended our framework to pancreas and prostate segmentation, and on both tasks, our model achieves competitive performance with state-of-the-art methods, while being substantially smaller and more efficient than foundation model variants. This demonstrates that our approach generalizes across diverse anatomical structures and imaging protocols, not just on multiple sclerosis lesions. Our framework offers significant computational efficiency. By eliminating SAM at inference, we achieve 7 times faster processing than AutoSAM and 15 times faster than MedSAM, with 5 up to 30 times fewer parameters. To wrap up, by decoupling inference from foundation models and automating prompt discovery, we enable scalable, accurate, and efficient segmentation, especially suited for resource-constrained clinical environments. Thank you for watching.